Yes, good evening. This is Sulaiman Kiggundu with my colleague Susan, and we're going to take you through machine learning.
My name is Twongiirwe Susan, and I'm going to take you the introduction part of machine learning. Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. Machine learning is a subset of AI, like artificial intelligence, and it focuses more on development of algorithms and models that allow machines to learn from experience and data. Why do we need machine learning? Machine learning, we use it mostly when we have complex tasks that require a lot of rules to be written. For example, image recognition. It's not as easy as to write commands for a traffic light where you have to like write the commands for the stop. When the color this comes on, you do this. When this color comes on, because there are the rules set. There are so few you can easily write them. But for machine learning algorithm here, we need like to continuously learn from the rules, like to continuously based on the data we have for us to solve the problem, which deals in having very many rules. That's why we need machine learning, because you continue doing something continuously, it becomes easier. Then we have types of machine learning. Machine learning has two types. For example, the first one is supervised machine learning, which requires a labeled data set. This one is necessary for supervision during training of a machine learning algorithm, and we can use regression and classification. And regression handles the continuous data type of numerical data. Classification deals mainly in categorical data that is exclusive from each other. And the other part of unsupervised machine learning, this one enables a machine learning algorithm to learn without any supervision. The machine learning algorithm to learn without any supervision, it means it will need some features to help it get more information. We have clustering, here is grouping together the features that show the same characteristic. And then we can even use anomaly detection. Here is detecting the unusual occurrence of the data instance, and you know this is not supposed to be it, or this is it. We can keep this or use this. We have a machine learning pipeline, which is the outlines or the steps of a machine learning algorithm, like for it to learn, which steps are we supposed to take. And step number one is get data. Here is literally organizing or getting the raw data relevant to the problem. Like, what do we need? What are we looking for? That is get data. Then perform the exploratory data analysis. Here you explore, you identify the patterns, which one is connecting to what. You find out, you explore the data you just collected. And then step number three, you prepare the data for the machine learning algorithm. Here is you pre-process, you clean the data, you know what to use it, like which one do you need specifically. Then you select the model you're going to use to train that machine learning algorithm. Then you can fine tune your model. Like you've already found out the model you want to use. So you use this particular model to do what you want to do, like no, like make the machine learn from the model. And step number six is present your solution. Now you know what you're looking for, you know what the problem is, and like you've figured out what you need to do. So you present what solution you can do, and then finally you launch and monitor and maintain your system. Then we have machine learning modeling. A model is a representation of some phenomenon. And we have three key things for a machine learning model. We have prediction model, cost function, and the optimizer. And basically, this machine learning model has two types of models, and one is probabilistic models and another one is deterministic models. And deterministic models has no randomness. You have to know exactly the exact relationship between something. There is no prediction error that is here. And then also probabilistic model, for it has randomness. It can be deterministic. You can have random error, and this probabilistic model has three types. We have regression models, correlation models, and other models. And under regression models, these ones specifically, they are used to represent the relationship between the dependent variable and an explanatory variable. And the steps for this regression modeling are hypothesize the deterministic component, specify the probability distribution of random error term, evaluate the fitted model, and then use the prediction and estimation. In a linear regression model, the relationship between variables is a linear function. The least squares help us to get the best fit line. Like when we are drawing graphs, and then you have different elements in that graph, but then you want to find out which one is nearer to which, you draw the best fit line, which differentiates between the actual y values and the predictable y values as the minimum. You can draw the line that is the best fit, and this line is going to help you know which one is predictable and which ones are the actual. And then we have a parametric model, which shows you exactly the data that will fit, and then the non-parametric model that tells you what the regression should look like. For the parametric, you know exactly what is going to fit, but the other one just gives you the overview of what it will look like. And then we have the k-nearest neighbors. The k-nearest neighbors have four attributes for the iris dataset, and the iris dataset itself, it's very classic. It is straightforward multi-class classification dataset, like classification category, and this has four attributes. And attribute number one is we have sepal length, sepal width, petal length, and petal width, and they are all measured in centimeters. Then we have the main steps of the k-nearest neighbors algorithm. You have to first calculate, your target, you have that one target you have, and then you have to know their neighbors. You calculate all the distances it is between, like, from it and its neighbor. You go through the whole training thing, and you know which one is which. Then after finding out the nearest by sorting them according to their distances, you can have the distance which is like 2, another one has like 5. So you're going to consider the 2, then you classify the point based on the majority vote. Which one is the nearest? Which one was your nearest? It's the one you consider. Then you can never tune the hyperparameters using the test data, because the ultimate goal of any machine learning algorithm is to perform well on the unseen data, the data we are not seeing. So the fact that we are changing the hyperparameters of the algorithm based on how well it has performed on the test contradicts the idea. So therefore, to avoid this, we have to use the Euclidean distance and Manhattan distance. And for us to use the Euclidean distance, the dimensions have to have the similar properties. That is when we are dealing with Euclidean distance. Then Manhattan distance, the dimensions are dissimilar. That's when we use it. Then for all the features are equally important, from all the scales, they must be normalized. For example, we have applications of the k-nearest neighbors. It's used mostly in text mining, agriculture, and finance. Then we have pros and cons, which are literally the advantages and disadvantages of k-nearest neighbors. And one of the advantages is it's so easy to explain, simple to understand, and extremely powerful. And the second one, it does not require assumptions of the data distribution. Okay, you don't have to even assume it's going to always be your first choice. Even if you have no knowledge on it, or you have very little knowledge of it, it is so easy to just hop on and use. Then we have, it can be used easily in the multi-class datasets. the disadvantages or the cons. You have efficiency of the algorithm declines very fast as it grows. It comes at a cost of making the prediction step. It cannot work if there are missing values. Then we have the Gini impurity. The Gini impurity measures the frequency at which any element of the dataset will be mislabeled when randomly labeled. The Gini impurity is the probability that any randomly chosen element from the dataset would be misclassified. You've labeled them, yes, but what is going to help us know that you've put it in a different or in a wrong set? And Gini score is from 0 to 5, 0.5. So the 0 means you have perfect impurity, which means all elements actually belong there. But then for the 0.5 means maximum impurity, the elements are equally split in all classes. And then the other thing used to measure is entropy. Entropy is used for the unpredictability or disorder in decision trees. It tells you the spread out and the different labels in a data set. For it ranges from 0 to 1. And when you're at 0, you have a perfect order or a pure node. And then when you're at 1, it means you have a maximum disorder completely mixed. So the fact that entropy uses logs and all that, it means the calculation of the Gini index will be very faster compared to that other one. Then the pros and cons of Gini of decision trees, we have easy to interpret and visualize. It has no assumptions. It can easily capture linear patterns. And then the disadvantages are sensitive to noisy data. The small variation can result in different decision trees. Greedy algorithms cannot yield. And that's all I had for you. My colleague can take over.
Good evening. Yeah, once again, I'm going to take you through assemble learning, and we're going to begin with the actual definition of assemble learning. Now, assemble learning is the is where is a strategy where multiple models are combined to create a single, more powerful model. This is where you train the models independently and then come up with something that is more robust. And there are two types of ensemble learning. We have bagging and we have boosting. Bagging is the parallel ensemble learning method designed to reduce variance. So bagging is mainly variance, and then boosting is the bias. And by variance, we are talking about the similarity between the two different models trained separately, and then the bias boosting is mainly dealing with bias because sequentially it's dealing with the same model, but we're improving the model to be better than the previous state at which it was. Key concepts to pick from here, we have other concepts like out of bag error. This is where this is a technique used in bagging, especially random forest, where bootstrap samples. These are samples. These are small samples. These are subsets of the original sample. So they are saying that bootstrap samples leave some data points. So out of bag error, these left out data points are used to verify their to provide they used to verify and reduce the bias in the different data sets. Then bootstrap sampling, we've already mentioned that this is the picking of different or subsets, like picking subsets from the original set. Then you train the subsets, or you work with the subsets and try to improve or bring try to treat to teach the models on those different sub until you come up with something more robust. Okay. So the other concept is random forest. And the random forest, I would say, we haven't talked about it. Random forest, this is the bagging, this is an algorithm used in bagging where a decision tree is used as a base learner. So here you get, as we said, bagging is parallel. So you get different subsets, and then you use them, you train them concurrently until you get something that is more robust, that is more standing. So here you get the different you get every subset and you use it as a tree. Then each subset is randomly, I mean, as you're making those selections, those decisions, you're using a decision tree. As you're making the decisions in the different bootstrap samples, you use a random selection. You randomly select the next splitting of that decision. So how we are then next we're having pros and cons of random forests. The pros you have reduces overfitting. How averaging predictions from multiple trees. So every time you pick from the different trees, you don't concentrate on one part. So it is in some way in some way avoiding that overfitting in one position. The other pro is it works with it handles large data, so large data sets. So it works with large data sets. Then it provides feature importance to useful in understanding impact variables. So the cons are it is also robust to outliers, whereby it puts in consideration the outliers and makes the decisions putting that into consideration, which is not on the other models. So the cons you have, it is biased to categorical variables, where like zip files where the data is grouped into many subsets. Then it is lower training, since you have to keep on splitting the different you keep on splitting the different decision trees. Then we're going to the next concept. We're having support vector mechanism. This is a mechanism. Support vector mechanism is a supervised learning algorithm used in classification and regression. The main aim of this is the main aim of doing this of the support vector mechanism is to find an optimal hyperlane that separates the data points of different classes. So with the maximum margin, so it has to draw a line between the different classes. Yeah. So there is two key terms that you need to know about these two. As you said, maximum margin. We use maximum margin where it doesn't leave any correlation or any similarities between the two data sets. And the soft margin, it could leave out some. It would pretend not to see the other some similarities between the two. So I think you get the difference between the soft margin and the hard margin. Then the explanation of SVM linearity and regression. For linear SMV, the algorithm finds a hyperlane in the original feature space to separate the classes. So I think that is clear enough. It finds a clear lane between the two. Then for nonlinear, the SMV uses the kernel function to transform data into higher dimension spaces, which it can become linearly separable. So sometimes the data is not separable. Then this SVM, it draws the line. It transforms the data using the k-mean from using the PCA, yeah, using the PCA to draw the line. I mean, to transform the nonlinear into linear that can be used. Then SMV regression support can also be used in regression tasks by finding functions that deviates by true target, by margin and tolerance. Yeah. Then the other concept is SMV cross-validation. SMV cross-validation is the splitting of data into training and validation. This is where you split data. The original data, you split part of it into the data that is going to be used for training. Then the other data will be used to prove whether what you've trained or the model has gained accuracy by checking on the data that was not used for training to see whether it is correlating. Then the other concept is data standardization, because machine learning, we had already talked about it. Data standardization is a process of technique